Under the coastline of southern Alaska, a slab of ocean floor is sliding underground at a pace slower than a fingernail grows, and that barely measurable motion is currently building one of the tallest, steepest mountain ranges on the planet. In the same narrow stretch of coast, ice is tearing that range back down at close to the same speed the rock is going up. Geologists who have spent years bolting instruments into the bedrock near Icy Bay and the St. Elias Mountains keep landing on the same uncomfortable pairing of numbers, checked one field season against the next. The peaks are rising by something on the order of 1/6 of an inch a year, and the glaciers grinding across them are cutting them down by roughly that same amount, so closely matched that the two rates cross back and forth across each other depending on which valley gets measured. Nobody designed that balance. It's closer to a machine caught in the act of building itself and demolishing itself at once. And Alaska is running several machines like that, stacked on top of each other, inside the same few hundred miles of ground, each one running fast enough that a working human career can watch it move. Stretch that 1/6 of an inch out across the full length of the St. Elias collision zone, and the volume of rock being pushed upward and ground back down in an average year becomes an amount of raw material in motion that'd be remarkable on its own even before anything else about this particular stretch of coastline gets mentioned. That's the real claim buried inside a title like this one, and it deserves to be checked rather than waved through, because insane is doing a lot of work for one word. Against an ordinary stretch of continental crust, most of the processes that shape a piece of land happen slowly enough that a human lifetime barely registers them. Mountains that grow at all tend to rise a few millimeters a year, an amount no unaided eye could ever confirm. Coastlines erode by inches a decade, changes that show up only when someone compares old surveys years apart. An earthquake above magnitude 8 arrives somewhere on Earth every few years on average, not inside one single sparsely populated state on a recurring basis, and a volcano capable of grounding transcontinental air traffic isn't supposed to sit less than a day's drive from a state capital. Alaska breaks that pacing across nearly every category a geologist can put a number on: uplift rate, erosion rate, snowfall, ice cover, earthquake size, volcano density, tidal range, permafrost extent, even the length of its own coastline. None of those sit near each other by accident. And none of them are simply Alaska being large, since plenty of large places on Earth are geologically calm for the same reasons this one isn't. Alaska is more than twice the size of Texas, big enough that the mechanisms driving its geography could plausibly vary by region without ever repeating themselves. And yet the same handful of causes keep resurfacing from the Panhandle to the Arctic coast, tying regions that share almost nothing else in common back to the identical few processes. They trace back to a small, specific set of physical causes that keep feeding each other. And once that chain is visible, the extremity in the title stops being an adjective and turns into something closer to a wiring diagram. One where pulling on any single wire visibly tugs at several others, whether that wire sits under a mountain, a coastline, or a single frozen village. Start with where Alaska actually sits, because the location is doing most of the work before a single measurement gets taken. The Pacific Plate, a slab of ocean floor bigger than the continental United States, is sliding northwest and diving underneath the much slower-moving North American Plate along a boundary that traces the whole southern edge of the state, from the Aleutian Islands out in the ocean to the Panhandle down near British Columbia. That's an ordinary subduction zone in the abstract sense. The Pacific coast of South America runs on the same basic principle, and so does Japan, and so does the Cascade Range further south along the same ocean. What makes the Alaska segment behave differently is a chunk of extra material wedged into the collision that's no business being there, arriving from somewhere else entirely, and a stream of moisture-loaded storms parked directly over the results almost year-round, both of which get explained fully in turn. The plate motion is the engine underneath all of it, so it comes first, And it's worth being precise about what that motion actually looks like in practice, rather than treating the plates are moving as a vague backdrop nobody bothers to picture. Picture what happens mechanically when a slab of old ocean floor meets a continent. Ocean floor is denser than continental crust, so at the boundary it usually loses the argument and bends downward, sliding beneath the lighter landmass into the mantle below. The line where that happens is a trench, and the friction along the buried interface is what produces the largest earthquakes on the planet because enormous slabs of rock lock together for centuries, store the strain, and then let go all at once. That locking and releasing sits underneath the seismic side of this story, and it gets its own turn later. For now, the important part is what subduction does above the surface. It drags the overriding continent's edge downward and compresses it sideways, and depending on what's riding along on the plate that's going under, that compression can build mountains, trigger volcanoes, or both at once. Along most subduction zones on Earth, the plate sliding under is fairly uniform old ocean floor, and the mountain building it produces is steady, predictable, and comparatively modest, spread evenly along hundreds of miles of coast. Southern Alaska got something else riding along on its conveyor belt, and the trench itself is worth pausing on before that passenger gets introduced. The trench marking this boundary is a landform in its own right, easy to forget about because almost nobody stands at the bottom of it. The Aleutian Trench plunges to nearly 5 miles below the ocean surface in its deepest sections, a gash in the seafloor deep enough to swallow Denali whole and still leave over a mile of water sitting on top of the summit. It runs for more than 2,000 miles, tracing the arc of the Aleutian Islands and marking the exact seam where the Pacific Plate bends downward and begins its descent into the mantle. Every process described from here forward, the mountains, the earthquakes, the volcanoes, ultimately answers to what's happening along that one buried seam, hidden underwater, dark and cold enough that it took modern sonar mapping to even confirm the trench's true shape. That pace of collision is fast by the standards of subduction zones generally, not just by the standards of everyday geology most people compare it against by instinct. The Juan de Fuca Plate, subducting beneath the Pacific Northwest along the Cascadia Zone that threatens Seattle and Portland, converges more slowly than the boundary running beneath southern Alaska, which is part of why the Cascade volcanoes erupt less often and why Cascadia's largest earthquakes are believed to arrive centuries apart rather than every few decades. A faster converging boundary delivers more strain more often to whatever sits above it. And it's one more reason this particular stretch of the Ring of Fire runs hotter, in almost every sense that matters, than most of the rest of it. Geologists call the extra passenger riding that plate the Yakutat terrain, a thick slab of old oceanic crust far removed from ordinary ocean floor, in places closer to 20 miles thick where typical ocean floor runs about 4 to 6, likely built up as a chain of undersea volcanoes and a plateau over tens of millions of years before it ever reached the coast it now collides with. Determining how thick that buried slab actually is required its own dedicated survey work, sending sound waves down through the water and the rock and timing how long the echoes take to bounce back off different layers, essentially building a cross-sectional image of buried crust the same way a doctor's ultrasound images tissue beneath skin. Thick, buoyant crust like that doesn't want to subduct the way thin ocean floor does. It resists going under, jams against the overriding plate, and instead of sliding cleanly into the mantle, it crumples, thickens, and shoves the crust above it upward, the geological equivalent of trying to force an object through a gap built for something thinner. That single piece of geological bad luck, a slab too fat to swallow, is the direct cause of the fastest uplift measured anywhere along this coast, and it explains why the mountains piled up exactly where they did, hugging the collision zone at Icy Bay and Yakutat, rather than spreading evenly along the entire plate boundary the way subduction-driven mountain ranges usually do elsewhere on the planet. The Yakutat Block didn't start out anywhere near Alaska either, which is part of what makes it such an unusual passenger to find riding this particular plate. Paleomagnetic readings taken from its rocks, essentially a record of which direction Earth's magnetic field was pointing at, the moment those minerals originally cooled and locked that orientation permanently in place, suggests the terrain formed well to the south and then rode northward along the coast for hundreds of miles over tens of millions of years before it ever reached the collision zone it occupies today. Some geologists reconstruct its origin as an unusually productive stretch of undersea volcanism, the kind of oceanic real estate that ends up thick and buoyant, almost by default, built the way a reef builds up over centuries rather than appearing all at once. By the time it finally jammed against the continent, it was carrying a geological history that had nothing to do with Alaska at all. A slab of crust dragged sideways into a collision that had go on to define a large share of the state's modern skyline millions of years after that crust first formed somewhere else entirely. A meaningful portion of that terrain hasn't even finished arriving yet. Geophysical surveys of the seafloor southwest of the current collision zone show more of the same thick, buoyant crust, still approaching the trench still years or millennia from actually jamming against the coast the way the leading edge already has. Whatever this machine is doing to the St. Elias Mountains today isn't close to a finished process. There's more collision already on its way, moving toward the coast at the same patient, inch-by-inch pace as everything else described here. The jam doesn't stay local, and that matters more than it might sound like at first, because the Yakutat Block is being shoved into the continent rather than sliding cleanly beneath it. The stress it generates has to travel somewhere, and it moves inland through a network of faults that reach hundreds of miles from the coast, the same way pressure applied to one corner of a rigid sheet transmits outward through the whole surface. The Denali Fault, which cuts across the interior of the state in a long, curving arc, is one of the main pressure release valves for that transmitted force. In 2002, a rupture along more than 200 miles of that fault produced a magnitude 7.9 earthquake, moving the ground by more than 20 feet in places during that single event, centered nowhere near the coastal collision zone. A plain reminder that whatever gets jammed at Yakutat doesn't stay Yakutat's problem. That one earthquake was only the latest entry in a much longer ledger, too. Geologists tracking distinctive rock units that appear on both sides of the Denali Fault, essentially matching puzzle pieces that once sat directly across from each other before the fault pulled them apart, have measured a cumulative lateral offset of roughly 200 miles accumulated over tens of millions of years of slower motion punctuated by earthquakes, exactly like the one in 2002. The fault has spent an immense stretch of geological time quietly filing entire chunks of Alaska's interior past one another, one earthquake at a time, far more than a crack that occasionally slips. And the whole interior of the state stays wired into the coastal collision even in places where the ground looks calm on the surface, and nobody would guess a jam 300 miles away was loading stress into a fault line under their own town. To put the uplift rate in context, it helps to compare it against places famous for building mountains the conventional way, through two entire continents grinding head-on into each other over tens of millions of years. The Himalayas, produced by India ramming into Asia, rise in some sectors at somewhere around 1/5 to 2/5 of an inch a year, among the fastest continental uplift rates documented anywhere on the planet. The benchmark geologists usually reach for first. The St. Elias Mountains, built by a single buoyant microplate jamming against a continental margin rather than a full continental collision, land in a comparable range. That's a strange result on paper. A relatively small, fast-moving slab of old ocean floor is punching in roughly the same weight class as the collision that produced Earth's tallest mountain range. And it's doing it in a fraction of the geological time, because the Yakutat terrain only started seriously colliding within the last several million years, a blink by the standards of plate tectonics, where most major mountain building takes tens of millions of years to fully play out from first contact to finished range. Denali itself, the tallest peak in North America, sits well inland from that direct collision. And its story runs through a slightly different mechanism, even though it belongs to the same larger system. Rather than sitting on top of the jammed terrain, Iwaydun Central Mankin Kabom, Denali rides along the same Denali Fault that released the 2002 earthquake, in a stretch where the fault bends and the surrounding crust gets squeezed and shoved upward as slices of rock grind past each other under compression. Measured from the plain, it rises out of to its summit at just over 20,000 feet. Denali's base-to-peak relief runs to roughly 18,000 feet because its base sits only a couple thousand feet above sea level to begin with. Everest, for comparison, climbs from a plateau already 3 miles in the sky, so despite being the taller mountain by total elevation above the ocean, its rise from base to summit works out closer to 12,000 feet. Denali isn't the biggest mountain on the planet. Measured the way a climber standing at its foot actually experiences it, its vertical wall of rock and ice is the tallest that exists anywhere entirely above sea level, a different question from which peak simply sits highest above the ocean, and one that matters more to the person actually walking uphill. Even that single most famous measurement changed as recently as 2015. When a United States Geological Survey team climbed to the summit and used GPS equipment to re-measure it directly, revising the accepted figure down by 10 feet from the number used for decades before that. A number that sounds like it should have been settled a century ago only became this precise within the last decade, thanks to the same GPS technology already tracking the ground's motion everywhere else in this account. Nearly every climber attempting Denali's most popular route starts by landing on the Kahiltna Glacier, the longest glacier in the Alaska Range. He's and spends the first several days of the expedition simply hauling sleds across the same kind of ice this whole account keeps returning to, crossing crevasses opened by ice flowing downhill under its own weight before the technical climbing has even begun. Denali doesn't stand alone in the range that carries its name either. Mount Foraker and Mount Hunter, both exceeding 14,000 feet, rise from the same uplifted crust along the same fault system nearby, close enough that climbers approaching Denali's base camp on the Kahiltna Glacier spend days walking in view of all 3 peaks at once, a cluster that'd anchor the skyline of most other mountain ranges on the continent and here amounts to Denali's immediate neighbors. The mountain scale has tested people directly for as long as anyone has tried to reach its summit. The first confirmed ascent, led by Hudson Stuck in 1913, took the climbing party weeks of exposure to the same wall of relief just described before they finally stood on top. That same relief and weather still makes Denali one of the more physically demanding mountains on the planet to climb despite its comparatively modest total elevation, with sudden weather changes and extreme cold claiming lives most years, and the National Park Service maintaining a dedicated mountaineering ranger program specifically to manage rescues on its slopes. Mount Logan, Canada's tallest peak, sits just across the border from the St. Elias Mountains, built by the exact same collision and the exact same uplift, a reminder that this machine doesn't recognize the political line running through the middle of it. Logan holds the largest base circumference of any non-volcanic mountain on the planet, a single massif so broad that its summit plateau alone stretches for miles, the direct result of the same buoyant jammed Yakutat slab pushing up an enormous volume of rock rather than one narrow peak. The mountains and ice already described sit largely inside Wrangell St. Elias National Park on the Alaska side, the largest national park in the United States by a wide margin, bigger than Switzerland, and roughly 6 times the size of Yellowstone, encompassing 4 separate mountain ranges within a single boundary. Most of it's no roads at all, reachable only by small aircraft or on foot, which is part of why so much of the fieldwork described throughout this account has taken researchers weeks of logistics simply to reach the rock they actually wanted to measure. Alaska's most extreme geography, in other words, doesn't stop cleanly at a state or national line. It just happens to have been the more famous half of a mountain building system that Canada shares equally. Not every mountain range packed into Alaska's borders belongs to this fast-moving, still-rising system. And it's worth flagging that early, rather than letting the title's momentum imply the whole state runs on one clock. The Brooks Range, up in the far north, formed from an entirely different, much older collision, one that happened over roughly 100 million years before the Yakutat terrain ever showed up on the scene farther south. Those peaks sit quiet today, worn down by ordinary weathering, rather than actively rising the way the St. Elias Mountains still are. That distinction gets its own fuller treatment later, but it matters now. Alaska's extremity comes from several separate machines, some ancient and mostly finished, some barely a few million years old and running at full tilt, rather than one continuous system running at the same speed under the entire state. Being Tsembustimwense, a coincidence of geography rather than of timing. Not every detail of this system is fully settled either, and the exact reason uplift concentrates so sharply along particular bends of the Denali Fault is one of the genuine open questions researchers are still working through. Some geologists point to the fault's own geometry, arguing that compression naturally piles up wherever the fault bends most sharply. Others point to deeper mantle flow, suggesting that the edge of the subducting Yakutat slab, hundreds of miles beneath the surface, is influencing surface uplift in ways current models don't yet fully capture. Both camps are working from the same GPS and seismic data. They simply haven't converged on the same explanation yet, which is a fairly ordinary state for an active research question, even one sitting directly beneath North America's tallest mountain. None of that mountain building would look the way it does without the second machine running directly on top of it. And this one starts in the ocean, rather than underground. The Gulf of Alaska sits beneath one of the most reliably stormy stretches of ocean on the planet. Driven by a semi-permanent low-pressure system meteorologists call the Aleutian Low, which pulls a steady conveyor of moisture-loaded air off the North Pacific and sends it straight into the coast, storm after storm, for most of the year, rarely giving the coastline more than a few calm days in a row, even in summer. Meteorologists have a specific term for how fast some of these storms intensify: bombogenesis, applied when a storm's central pressure drops by a defined threshold within 24 hours, essentially strengthening from an ordinary system into a full-blown, hurricane-force cyclone over the course of a single day. The Gulf of Alaska sees this kind of rapid intensification more often than almost anywhere else on the planet's storm tracks. One more reason the moisture arriving at the coast doesn't come gently, spread out over a week, but slams in fast. In short, intense pulses the mountains then have to absorb all at once. When that wet air runs into a wall of newly built, rapidly rising mountains, it's nowhere to go but up. And rising air cools, and cooling air dumps whatever moisture it was carrying, sometimes within a matter of hours of first making landfall. The mechanism has a name, orographic lift, and it's the same basic reason Seattle stays famously damp while the interior of the continent stays dry. In Alaska, the effect gets turned up because the mountains being hit are some of the youngest and steepest anywhere on the boundary, so the moisture gets wrung out with unusual force in a narrow band right at the coast, rather than being spread more gently across a wider, gentler slope the way it'd be against an older, worn-down range that's had tens of millions of years to soften its own angles. The numbers on either side of that mountain wall make the mechanism impossible to miss. Around Cordova and Prince William Sound, on the wet side, annual precipitation can run past 150 inches a year, genuine rainforest territory, thick with hemlock and spruce, standing in near constant drizzle for most of the calendar and moss climbing every surface that holds still long enough. Cross the Alaska Range into the interior around Fairbanks, and the same storm systems have already given up almost everything they were carrying, leaving a climate that receives closer to 10 or 12 inches of precipitation a year, dry enough to technically qualify as desert by the standard climate classification used anywhere else on the planet. One moisture-loaded weather system runs headlong into one freshly built mountain wall, and the wall wins decisively, stripping the air of nearly everything it carried before it ever reaches the far side. Denali itself sits close enough to the crest of that mountain wall that it still intercepts enough moisture to carry its own glaciers despite sitting at the edge of the dry interior. A reminder that the rain shadow line isn't a single clean wall so much as a gradient. With the tallest peaks along it still catching plenty of snow, the lower interior just beyond them will never see. It's a rain shadow effect sharper than almost anywhere else in North America. Sharp enough that the two climates sit less than a day's drive apart. Thompson Pass just outside Valdez has recorded some of the highest seasonal snowfall totals anywhere in the United States, including a single winter in the early 1950s that piled up more than 900 inches, a season's accumulation tall enough to bury a 6-story building, produced by the exact orographic collision between Gulf of Alaska moisture and freshly built coastal mountains just described. That same snowfall, landing on some of the steepest coastal terrain anywhere, has since made the mountains around the pass a destination for extreme skiing and snowboarding. Athletes flown in by helicopter specifically to ride slopes whose angle and snow depth exist because of the identical orographic collision responsible for the record totals themselves. The ocean moderates temperature just as directly as it delivers moisture, through a completely separate mechanism. Sitka, sitting on the open Pacific side of the Panhandle, rarely experiences the deep winter cold that grips the interior only a few hundred miles away, kept mild through the winter by the same relatively warm coastal water feeding the Aleutian Low's storms. A maritime buffering effect working through temperature rather than moisture. Neertsandborshire, distinct from the orographic story just described, but running on the same ocean. That same continental trapping shows up in the temperature record too, and the specific numbers are worth naming rather than rounding into a generic swing. In 1971, a research site at Prospect Creek in Alaska's interior recorded a low of roughly 80 degrees below 0 Fahrenheit, the coldest temperature ever officially measured anywhere in the United States. Fort Yukon, not far away, has recorded a high near 100 degrees Fahrenheit in summer, set back in 1915, a reading that wouldn't feel out of place in the American Southwest. The same general stretch of interior Alaska, cut off from the ocean's moderating influence by the same mountain wall already described, is capable of producing both of those extremes, sometimes within the same calendar year. An unusual range for any inhabited part of the planet outside the deep interior of Siberia. The mountains that build the rainforest on one side are, at the exact same time, manufacturing a near-Siberian continental climate on the other. And both outcomes come from the identical mechanism working in opposite directions on either side of one wall of rock. All of that wrung-out moisture has to land somewhere. And on the coastal side of the mountains, cold enough temperatures mean a large share of it lands as snow rather than rain, which sets up the third machine. Snow that survives a summer without fully melting compresses under the weight of the layers piling up above it, squeezing out air pockets and slowly turning into a denser, grainier material called firn. And firn that survives several more years compacts further into solid glacier ice, dense enough by then to appear blue in cross-section, because it's squeezed out nearly every trapped air bubble that once made it look white. Ice built this way keeps its own calendar too. Layers within ice fields like the Bagley, or the Summit Ice Cap on Mount Logan just across the Canadian border, preserve a year-by-year record of snowfall, temperature, and even volcanic ash from eruptions like Novaruptas, trapped in distinct bands the way tree rings record a forest's history. Researchers drilling ice cores from sites like these have reconstructed centuries of regional climate history directly out of layers most people would only ever see as an undifferentiated wall of white. It's a slow transformation, decades in most places, but repeat it year after year across a coastline that receives some of the heaviest snowfall on the continent. And the ice doesn't just accumulate, it starts to flow, dragged downhill under its own weight the way any sufficiently thick, sufficiently patient fluid eventually moves, however solid it feels underfoot. The scale that process reaches in Alaska is difficult to hold in the head using ordinary comparisons. More than 100,000 glaciers cover roughly 5% of the state's total land area, and a handful of them individually outsize entire smaller states. The Malaspina Glacier, spreading out where the St. Elias Mountains meet the coast near Yakutate, is a Piedmont glacier, meaning it's flowed out past the mountains and spread across the lowland in a wide fan rather than staying confined to a valley, and it covers more ground than the state of Rhode Island. It's fed in part by the Bagley Ice Field, a river of ice more than 100 miles long sitting in a trough carved between two mountain ranges, itself one of the largest subpolar ice fields outside the polar regions, and thick enough in places that the bedrock underneath has been pressed down by the sheer weight of ice sitting on top of it, a depression that'll only fully rebound long after the ice above it's gone. Malaspina itself has its own history of surging, much like Bering and Hubbard farther down the coast, its ice periodically speeding up and buckling its own surface into wide, looping folds visible clearly from the air, a wrinkled pattern left behind by decades of alternating fast and slow flow rather than by any single event. Some sections of the ice fields feeding these glaciers are estimated to run more than 1,000 feet thick, deep enough that the ice alone could bury a 60 or 70-story building before the actual bedrock underneath even begins. Not every glacier in this system behaves the same predictable way, and the Bering Glacier illustrates a stranger side of the machine. Sprawled along the coast east of Prince William Sound, it's the largest glacier by area in North America, feeding a proglacial lake called Vitus Lake at its terminus. And periodically it does something most glaciers never do. It surges, advancing suddenly by hundreds of feet a day for months after decades of comparative calm, likely driven by changes in how meltwater drains beneath the ice, rather than by any change in snowfall or air temperature. A surge can shove the glacier's leading edge forward by miles within a single season, and then the whole system quietly settles back into slow retreat for another few decades before doing it again. As unpredictable in its timing as it's dramatic once it starts. It's a useful reminder that this ice sheet isn't a steady, predictable machine running at one constant rate everywhere. Parts of it store energy and release it in fits, the same broad pattern the tectonics and the earthquakes follow at a completely different timescale, further down this same story. Further down the coast, the Juneau ice field feeds roughly 40 glaciers, including the Mendenhall Glacier, which sits close enough to Alaska's state capital that residents can watch it change from one year to the next, rather than take a geologist's word for it. Mendenhall has retreated more than 2 miles since it last stood at its maximum extent during the Little Ice Age, a cooler stretch that ran roughly from the 14th century into the 1800s, and the retreat has accelerated within living memory rather than slowing down. Photographs taken from the same fixed viewpoint a few decades apart show open water and bare rock where solid ice used to fill the entire frame, a comparison striking enough that it's become one of the more commonly cited visual records of glacier change anywhere in North America. It's one of the few places in this whole system where the underlying machine, glaciers, responding to a shifting balance between snowfall and melt, shows up on a timescale a person can actually watch, rather than one that only appears in GPS data or sediment cores, pulled up by researchers with drilling equipment. The Kenai Peninsula carries its own version of this same ice machine in the Harding Ice Field, a broad, nearly unbroken plain of ice, roughly the size of Rhode Island in its own right, sitting high enough and, cold enough that only isolated mountain peaks called nunataks poke up through its surface. Exit Glacier, one of the ice field's outlet glaciers, is unusually easy to reach. A short trail leads hikers directly to its face, and the National Park Service has posted a series of dated signs along that trail marking exactly where the ice stood in past years: 1899, 1961, 2005, each sign standing further from the current ice edge than the last one before it. Walking that trail means walking through more than a century of retreat measured out in minutes rather than in field seasons. One of the only places in this whole system where the pace of the machine becomes something a visitor can experience directly, rather than something described secondhand by an instrument. 3 separate factors have to line up for ice to pile up at this scale, and Alaska happens to run all 3 simultaneously in the same stretch of coast. It needs storms carrying enough moisture to dump extraordinary volumes of snow, which the Gulf of Alaska supplies through the Aleutian Low. It needs mountains tall and steep enough to force that moisture out of the air efficiently, which the Yakutat Collision supplies through unusually fast uplift. And it needs air cold enough for enough of the year that the snow doesn't simply melt away before it can compact into ice, which the latitude and the elevation both supply together, each covering for a weakness the other alone would leave exposed. Remove any one of the 3 and ice this size doesn't exist. A wetter but flatter coastline would just be rainy. A tall but dry mountain range would stay mostly bare rock. Alaska has all 3 dials turned up at once, and the glaciers are simply the visible readout of that alignment, a kind of geological coincidence detector running continuously along the coast. A global effort called the Randolph Glacier Inventory has used satellite imagery to catalog and outline the boundary of essentially every glacier on the planet, Alaska's more than 100,000 included, giving researchers a consistent, comparable baseline against which every future satellite pass can measure exactly how much each one has changed. Ice sitting on a mountain isn't a passive weight either. A temperate glacier, meaning one warm enough at its base to have liquid meltwater running underneath it, is one of the most efficient erosion tools nature has, more aggressive per year than a comparable stretch of an ordinary river or an ordinary rock slide, left to work on its own over the same span of time. Meltwater seeps down through cracks in the ice to the bedrock below, lubricates the interface between ice and rock, and lets the whole mass slide, rather than merely creep the way colder, drier polar ice tends to. As it slides, the glacier plucks and quarries chunks of rock loose from its bed, then grinds them against the surface underneath in a process that produces a fine, pale sediment nicknamed rock flour, so abundant that rivers fed by these glaciers often run milky gray or turquoise, carrying pulverized mountain in suspension rather than clear water, visible from the air as pale ribbons threading through darker, sediment-free tributaries. That same fine, mineral-rich sediment does more than tint a river a certain color. In the Matanuska Valley northeast of Anchorage, Hisis Wandanalims, glacially ground silt deposited across the valley floor over thousands of years produced some of the most fertile farmland in the state, productive enough, combined with nearly 20 hours of summer daylight at that latitude, to grow cabbages that regularly reach 70 or more pounds at the valley's annual state fair. It's an almost incongruous outcome to trace back to a process introduced mostly through mountains and erosion. The same grinding that produces hazard and spectacle elsewhere in this account also quietly produces some of the best soil in the state, exactly where it happens to settle. A glacier of this kind can strip rock away at a rate that rivals or even exceeds the pace of the fastest tectonic uplift on the planet, which happens to be exactly the collision playing out in this specific spot, underneath this specific ice. That's where the opening measurement stops being a curiosity and turns into the explanation the rest of this has been building toward. Researchers working through a collaboration known as the St. Elias Erosion and Tectonics Project, including geologists like Terry Pavlis and Sean Gulick, spent years drilling sediment cores, mapping fault lines, and tracking glacier flow specifically to test whether uplift and erosion in this range were actually connected or simply happened to land in a similar ballpark by coincidence. The kind of question that sounds almost unanswerable until you've got decades of instrument data to compare. What they found looked closer to a feedback loop than a coincidence. Rapid uplift builds steep terrain. Steep terrain feeds and accelerates glaciers. Aggressive glacial erosion strips mass off the range faster than gentler erosion ever could manage, and removing that mass changes the pressure on the crust below in a way that appears to draw the deep rock upward even faster, refilling what the ice just carried away almost as quickly as it left. Push the mountains up, and the ice answers by cutting harder. Cut the mountains down, and the crust answers by rising faster to replace what left. Neither side of that exchange is winning, and neither is really losing either. It's a system holding itself in a kind of violent equilibrium, fast enough that instruments bolted into the rock today can measure the tug of war in something close to real time, the same way you could weigh a boxer's punch against the exact counterpunch that lands a half-second later and call the fight, roughly, a draw. Some of the most direct evidence for that connection came from an ocean drilling expedition that sailed specifically to test it. In 2013, the research vessel JOIDES Resolution, operating under the International Ocean Discovery Program, drilled sediment cores from the floor of the Gulf of Alaska itself, pulling up a continuous record of exactly how much material this coastline has shed into the ocean over roughly the last million years. Sediment piling up that thick, that consistently, only makes sense if erosion onshore has been running about as fast as the uplift feeding it, turning a hypothesis about two competing forces into something confirmed by material physically pulled up from the seafloor and examined under a microscope. Two of Alaska's glaciers, Wolverine Glacier near Prince William Sound and Gulkana Glacier in the eastern Alaska Range, Inichinsakenchi Shinoashkrines, have been measured every single year since 1966 under the United States Geological Survey's Benchmark Glacier Program, among the longest continuously monitored glaciers anywhere in North America. Researchers return to the same stakes drilled into the ice each spring and each fall, measuring exactly how much snow accumulated and how much ice melted away, building a year-by-year ledger precise enough to separate an ordinary cold or snowy year from a genuine long-term trend. That 6-decade record is a large part of why scientists can say, with real confidence rather than impression, how fast this particular machine has been running compared with decades past. Alaska isn't literally the only place on the planet where researchers have measured this tug-of-war between mountain building and glacial erosion directly. New Zealand's Southern Alps, produced by a different plate boundary entirely, show a broadly similar coupling between rapid uplift and aggressive erosion by ice and rivers, and work on that range helped establish the basic idea that erosion itself can influence how fast a mountain grows, not merely how fast it wears back down afterward, a counterintuitive finding when it first started circulating among geologists. What sets the St. Elias Mountains apart, even against that comparison, is speed. The uplift rates measured here are among the fastest documented anywhere outside a full continental collision, and the glaciers doing the cutting are unusually large relative to the size of the mountain range feeding them, which is exactly the combination that let researchers measure the connection with unusual clarity here, rather than having to infer it indirectly from rock that finished this particular argument millions of years ago and left only the scars behind. Measuring an erosion rate at all requires its own kind of cleverness, since nobody can weigh a mountain before and after. Researchers instead rely on cosmogenic nuclide dating, measuring rare isotopes that build up in a rock's surface only while it sits exposed to cosmic rays raining down from space. A rock that's been eroding quickly, Constantly having fresh surface exposed as the layer above it gets stripped away accumulates far less of that isotopic signature than a rock that's sat untouched for millions of years. And comparing the two lets geologists calculate an average erosion rate for an entire drainage basin from a single handful of sediment collected at a river mouth. The sediment that erosion produces has to go somewhere, and following it downstream fills in the next piece of the coastline's shape. Glaciers that reach the sea, known as tidewater glaciers, calve enormous slabs of ice directly into the ocean, and the sound arrives before the eye can fully register what caused it. A crack like close thunder as thousands of tons of ice shear away from the face and drop into the water, followed by a wave that can rock or even capsize a small boat anchored too close. And then, often, a long quiet, while the newly exposed ice face keeps dripping meltwater into the sound below. The fjords these glaciers carve on the way there, deep, steep-walled inlets gouged by ice that's since retreated, define much of the coastline from Prince William Sound down through the Panhandle. The Columbia Glacier near Valdez has retreated more than 12 miles since the 1980s, exposing a fjord that ice had occupied for centuries beforehand, while the nearby Hubbard Glacier periodically does something close to the opposite, surging forward and occasionally threatening to seal an entire inlet shut with ice. It's actually done exactly that, more than once. In 1986 and again in 2002, Hubbard Glacier's advancing front pushed far enough across the mouth of Russell Fjord to seal it off completely, damming an entire arm of the ocean behind a wall of ice and turning it into a rapidly rising, landlocked lake within a matter of weeks. On both occasions, the ice dam eventually failed under the pressure of the trapped water building up behind it, releasing the lake in a sudden, catastrophic flood back into the sea, a type of event glaciologists call a jökulhlaup, borrowing the Icelandic term for exactly this kind of ice-dammed outburst. Wildlife trapped in the fjord while it was still open ocean, including harbor seals that had moved in during the calm months, had to adapt to a body of water that could vanish within days of the dam finally giving way. Retreat and advance aren't contradictory outcomes inside this system. Both are the same underlying machine responding to slightly different local balances between how much snow falls in the accumulation zone above and how much ice gets lost to melting and calving below, and either direction, patient or sudden, permanently reshapes the coast it happens along. There's a second, quieter consequence of all that ice loss that most descriptions of Alaska skip entirely, and it deserves its own moment because the scale of it's strange. When a heavy weight is removed from the crust doesn't stay exactly where it was, it rebounds, the same way a mattress rises back up after someone gets off it. And that process, called isostatic rebound, is usually associated with places that were crushed under continental ice sheets during the last ice age and have spent the past 10,000 years or more slowly springing back, at a pace measured in fractions of an inch annually, barely worth mentioning in a single human lifetime. Around Glacier Bay, in the same collision zone already doing all this other work, GPS stations bolted into the bedrock have measured the ground rising by more than an inch a year in places, among the fastest rates of present-day uplift recorded anywhere on the planet. Ordinary post-Ice Age rebound elsewhere on Earth traces back to continental ice sheets that finished melting 10,000 years ago. This rebound is driven by glaciers actively thinning right now, within the working lifetime of the researchers measuring them. Researchers, including glaciologist Christopher Larson, have tied that rebound directly to measured ongoing ice loss in the surrounding ice fields, close to real time, rather than to a slow leftover from an ice age everywhere else on Earth finished responding to long ago. Glacier Bay National Park alone draws a substantial share of the roughly 1 million cruise ship passengers who visit Alaska's coast each year. An entire tourism economy built directly on top of scenery that exists only because of the specific combination of uplift, precipitation, and ice already explained across this account. Ice did something to Alaska's geography on an even larger scale than any single glacier, too, and it happened during the broader ice ages rather than through local mountain glaciation alone. When continental ice sheets locked up a substantial share of the planet's water as ice during the last glacial maximum, global sea level dropped by more than 300 feet compared to today, low enough to expose a wide plain of dry land connecting Alaska to Siberia, across what's now the floor of the Bering Strait. Researchers call that exposed plain Beringia, and for thousands of years it stood as an ordinary, if cold, stretch of tundra rather than a strait at all. Wide enough in places that anyone crossing it on foot might not have realized they were walking between two continents rather than simply moving across open ground. Genetic and archaeological evidence both point to Beringia as the route the first human populations used to reach the Americas, more than 15,000 years ago by most current estimates, which means Alaska's landscape didn't just get shaped by ice, it briefly became a bridge because of it. A role written entirely by how much water the planet had frozen into ice sheets thousands of miles away at the time, with no local Alaskan process required to make it happen. Nearly everything named Bering in this account, the strait, the sea, the land bridge, traces back to one person, navigator Vitus Bering, who led the Russian expedition that first charted much of this coast for Europe in the 1740s. Mount St. Elias itself, at the heart of the mountain range already covered, got its name from that same expedition, sited and named on the Orthodox feast day of St. Elias in 1741, the first documented European sighting of any part of what's now Alaska. The Bering Sea carries its own imprint of that same Ice Age history. Much of its floor sits on a broad, unusually shallow continental shelf, the very ground that stood exposed as dry land when sea level dropped during the Ice Ages, and today that shallow shelf makes the Bering Sea one of the most biologically productive stretches of ocean on the planet, since sunlight can reach nutrient-rich water near the seafloor far more easily than it can across a typical deeper ocean basin. A significant share of the entire United States seafood catch, including much of its pollock, crab, and cod, comes out of these waters. An economic engine resting directly on geography that a lower sea level, tens of thousands of years ago, happened to leave shallow enough for a productive ecosystem to make full use of it today. Alaska's glaciers matter well beyond the state's own coastline for a second, more modern reason. Although they hold only a small fraction of the world's total land ice compared with the ice sheets covering Greenland and Antarctica, research led by glaciologist Anthony Arendt and colleagues found that Alaska's glaciers have been thinning fast enough to rank among the largest single contributors to global sea level rise from mountain glaciers anywhere on the planet, punching well above their share of the world's total ice volume. The same combination of heavy snowfall, young, steep mountains, and a warming climate that makes this ice machine so productive also makes it unusually quick to lose mass once the balance tips toward melting, and sustained measurement has shown exactly that happening here for decades running. If every glacier in the state melted completely, researchers estimate the water released would be enough to raise global sea level by close to half an inch on its own. A striking figure for ice, covering only about 5% of a single state's land area. Everything described so far, the uplift, the mountains, the storms, the ice, the erosion, and the rebound, all sits on top of the same locked boundary between two plates, and that boundary has a separate, far more sudden way of releasing the strain it builds up, which is where the seismic side of this story starts in earnest. Along most of a subduction zone, the interface between the sinking plate and the plate above doesn't slide smoothly. Friction locks the two together across a broad patch, sometimes hundreds of miles long. And as the plates keep converging underneath that locked patch, Stress accumulates the way a bent stick stores energy before it snaps, quietly, for decades or centuries at a stretch, with nothing visible happening at the surface to mark the buildup. When a locked segment finally slips, it doesn't slip gently. It releases everything stored across the whole patch at once. And the larger the locked area, the larger the earthquake it becomes capable of producing. On the afternoon of Good Friday in 1964, a stretch of that locked boundary beneath Prince William Sound let go all at once, producing a magnitude 9.2 earthquake, the second largest ever recorded by modern instruments anywhere on the planet. Shaking near the epicenter lasted somewhere around 4 to 5 minutes, long enough that some survivors later said they genuinely believed the ground would never stop moving, that the shaking itself had simply become the new, permanent condition of the world. The rupture didn't just shake the surface, it physically moved it. Geologist George Plafker, sent by the United States Geological Survey to map the aftermath, spent months documenting land that had permanently risen or sunk across a region roughly the size of California, walking beaches and river mouths with survey instruments to chart exactly how far the ground had shifted in either direction. Parts of Montague Island rose more than 30 feet in a matter of minutes, dry land where there had been shoreline the day before, while the town of Portage sank low enough that it flooded permanently with every high tide and had to be abandoned outright, its buildings left standing in salt water for years afterward as a visible reminder of what the ground beneath it had done. The shaking itself caused only a fraction of the earthquake's roughly 130 deaths. Most came from the tsunami that followed, including a wave triggered by an underwater landslide that tore away Valdez's original waterfront, while dock workers and onlookers had gathered nearby to watch a cargo ship unload, forcing the entire town to be rebuilt on more stable ground several miles from where it had always stood. Several of Valdez's more solid buildings were literally jacked up, set on rollers, and hauled overland to the new site rather than rebuilt from scratch, a rare case of part of a community moving with some of its original walls still standing. Kodiak Island, closer to the rupture in some respects than Prince William Sound itself, took some of the tsunami's worst damage directly, losing much of its downtown and a large share of its fishing fleet in a single night, its own land level shifting permanently the same way the rest of the regions did. The human cost fell hardest of all on some of the smallest communities directly in the tsunami's path. The Sugpiaq village of Chenega, close to the earthquake's epicenter, was struck by a wave within minutes of the shaking itself before any warning could possibly have reached them, and a large share of the village's population died that afternoon. Survivors eventually rebuilt the community at a new, safer site years later, but Chenega's losses remain one of the starkest human costs anywhere in this whole account. Anchorage took a direct hit from the same earthquake, and the mechanism behind its worst damage adds one more wrinkle to the story. A layer of sensitive clay called Bootlegger Cove clay sits beneath parts of the city, stable under normal conditions, but prone to sudden strength loss once shaken hard enough. During the quake, a stretch of bluff above Cook Inlet known as Turnagain Heights failed catastrophically along that clay layer, an entire neighborhood sliding and breaking apart as the ground beneath it turned briefly into something closer to a fluid than a foundation. Roughly 75 homes were destroyed in that single landslide, and the scarred, uneven ground it left behind was eventually set aside rather than rebuilt on, turned into a public park that still carries the shape of the failure in its rolling terrain today. The earthquake left a quieter, stranger mark near Turnagain Arm that still stands as well. Where the ground subsided during the quake, saltwater began flooding areas that had previously been dry forest, and the trees there died where they stood, killed by salt rather than by fire or storm. Decades later, the bleached, bare trunks of those same trees are still visible rising out of the tidal flats, a phenomenon locals and scientists alike call a ghost forest, a permanent, unmoving record of exactly how far the ground dropped in a few minutes back in 1964. The rupture's reach went well beyond even that, Seismic waves traveling outward from the fault lines sloshed water measurably in wells and swimming pools as far away as Texas and Louisiana, thousands of miles from the epicenter, a phenomenon called a seiche, caused by long, slow ground waves setting standing water gently rocking long after the shaking itself would have been far too faint for anyone that far away to actually feel. The wave didn't stay confined to Alaska either. It crossed open ocean and struck Crescent City, California, more than 1,500 miles away, killing 11 people and destroying a significant part of the town's waterfront, proof that a rupture along one specific stretch of Alaska's coast could take lives on a beach whose residents had never even felt the earthquake that caused it. Magnitude doesn't behave the way most numbers do. And getting that scale right is the only way any of these comparisons actually mean what they sound like they mean. Each whole step up the magnitude scale represents roughly 32 times more energy released, a multiplication rather than a simple percentage increase. So the gap between a magnitude 7 and a magnitude 9 isn't a modest jump. It works out to somewhere on the order of 1,000 times more energy locked into a single rupture. Measured against that scale, 1964's magnitude 9.2 didn't just edge out an ordinary large earthquake. It released something in the range of 1,000 times more energy than the magnitude 7.1 earthquake that shook Anchorage 54 years later, an event covered shortly, despite both registering as unmistakably massive to anyone who actually lived through either one. Much of the seismic monitoring behind these numbers runs out of the Alaska Earthquake Center at the University of Alaska Fairbanks, which operates a network of seismometers spread across the state specifically because a rupture here can go from first detection to a tsunami, reaching an occupied shoreline in a matter of minutes, leaving almost no room for a slow analysis process. The same institution's Geophysical Institute coordinates volcano monitoring, GPS geodesy, and satellite radar analysis, sensitive enough to detect a volcano's summit swelling by a fraction of an inch before it ever erupts, which is often the only warning anyone gets before ash reaches an aircraft's flight path. The observatory communicates that hazard through a simple color code: green for normal background activity, yellow for elevated unrest, orange for an eruption that's likely or already underway with limited ash, and red for a significant ash-producing eruption, a system built specifically so a pilot or an airline dispatcher can make a fast decision without needing to interpret raw seismic data themselves. That single earthquake did more than reshape a stretch of coastline. Placker's uplift mapping, showing a clean, continuous pattern of the coast tilting up on one side of a line and down on the other, became some of the most convincing physical evidence supporting the then new and still contested theory of plate tectonics, at a moment when a meaningful share of geologists weren't yet convinced continents actually moved at all, let alone that whole plates could lock, bend, and snap back the way this earthquake demonstrated in front of instruments for the first time. An earthquake most people think of purely as a disaster also became one of the pieces of evidence that helped settle a genuine, decades-long scientific argument about how the entire planet works underneath its own surface. The tsunami it produced also exposed how little warning coastal communities had before a wave like that arrived, and that gap led directly to what eventually became the National Tsunami Warning Center, headquartered in Palmer, Alaska, tasked with monitoring seismic activity across the whole Pacific Basin and issuing alerts fast enough to actually matter. A warning system that now protects coastlines from Hawaii to Japan exists, in a very direct sense, because of what this one stretch of Alaska coastline did on a single afternoon in 1964. Coastal communities across this stretch of Alaska now live with that hazard built into daily infrastructure, rather than treated as a distant memory. Towns including Kodiak, Seward, and Sitka maintain marked tsunami evacuation routes leading to higher ground, along with siren systems tested on a regular schedule, precautions that trace their existence directly back to lessons the region learned the hard way that Good Friday and has kept updating ever since. 1964 wasn't a freak event along this boundary. It was one entry on a short list of the largest earthquakes ever instrumentally recorded anywhere on Earth. And remarkably, 3 of them trace back to the same Aleutian, Alaska subduction system. The 1957 Andreanof Islands earthquake in the magnitude 8.6 range and the 1965 Rat Islands earthquake, close to magnitude 8.7, both ruptured segments of the same plate boundary within less than a decade of each other. No other single fault system on the planet has produced that many of history's largest instrumentally recorded earthquakes in such a short span. It's a large part of why Alaska, despite its comparatively small population, is consistently ranked as the most seismically active state in the country, and why it registers a disproportionate share of the world's total earthquake energy release in an average year. Quietly, out along a coastline, most of the country never thinks about between disasters. Instruments across the state record something on the order of 40,000 earthquakes in an average year. The overwhelming majority too small for anyone to feel, but a rate high enough that seismologists monitoring Alaska are never really looking at a quiet baseline the way monitoring networks in most other states are. The ground here is essentially never fully still, even on the days nothing makes the news. The subducting plate itself explains something beyond raw earthquake size too, where those earthquakes happen at different depths. Close to the coast and the trench, earthquakes stay shallow, breaking within the top few miles of crust. Move further inland, and earthquakes occur progressively deeper, tracing the same subducting slab as it continues its descent hundreds of miles beneath the interior, a pattern seismologists call a Wadati-Benioff zone, after the 2 researchers who first identified it decades ago. Reading the depth of an earthquake on a map is, in a real sense, reading how far down the buried plate happens to sit at that exact point, turning an ordinary earthquake catalog into an indirect map of a slab nobody has ever drilled through directly. Not every mile of this plate boundary works the same way either, and the differences matter as much as the similarities. Along the Alaska Panhandle, southeast of the main subduction zone, the Pacific and North American plates stop diving past each other vertically and instead grind sideways along a more or less vertical boundary called the Fairweather Fault, a transform fault built on the same basic principle as California's San Andreas, rather than the subduction mechanics driving the rest of the coast. Sideways motion produces its own kind of earthquake, and on the 9th of July in 1958, a rupture along that fault, estimated at magnitude 7.8, triggered something almost nobody expected. The shaking dislodged an enormous mass of rock, on the order of 40 million cubic yards, from a mountainside above Lituya Bay, and the entire mass slammed into the water below in a matter of seconds. The impact displaced water with such force that it produced a wave scouring vegetation and soil off the opposing mountainside up to a height of roughly 1,700 feet above the bay, the tallest wave ever documented anywhere on Earth, confirmed afterward by geologist Don Miller of the United States Geological Survey. Through the stripped, bare trim line, the water left behind on the surrounding slopes for years. Researchers reconstructing this coastline's earthquake history further back than any written record allow rely partly on lake and fjord sediment cores, where a sudden earthquake can trigger an underwater landslide that deposits a distinctive disturbed layer called a turbidite sandwiched between the normal, gradually accumulated mud on either side. Counting and dating those disturbed layers lets geologists build a timeline of major earthquakes stretching back thousands of years before anyone was around to record one directly. Extending case studies like this one and 1964 into a much longer pattern than living memory alone could ever supply. 3 fishing boats happened to be anchored in the bay that night. 2 rode the wave out and survived. The third was lost with both people aboard. It stands as one of the starkest reminders in this whole account that a single earthquake, even one confined to a fault most people outside Alaska have never heard of, can convert directly into a hazard that's nothing to do with shaking at all. Not every dangerous earthquake this system produces ruptures the same way 1964 or 1958 did, and a much more recent event shows a third mechanism at work. On the last day of November in 2018, Anchorage was shaken by a magnitude 7.1 earthquake that started roughly 30 miles beneath the city, deep inside the Pacific Plate itself, rather than along the shallow, locked interface between the two plates or along a surface transform fault. Geologists call that kind of event an intraslab earthquake, caused by the sinking plate fracturing internally as it bends and stretches on its way down, a distinctly different mechanism from either of the two already described, even though all three trace back to the same underlying subduction system in the end. The shaking buckled a highway off-ramp near the airport and caused waterlogged soil across parts of the city to temporarily lose its solid behavior in a process called liquefaction, cracking foundations and roads throughout the area. Remarkably, given the intensity of the shaking, no one died, in part because building codes tightened in the decades after 1964 had done exactly what they were designed to do when the moment finally arrived. Decades later than anyone who wrote those codes could have specifically predicted, roughly 40% of Alaska's entire population lives in and around Anchorage, which means a substantial share of the state sits directly inside the Foreark Basin, shaped by the same subducting plate responsible for these earthquakes, on soils already shown to be vulnerable to liquefaction within range of ash from more than one historically active volcano. The extremity described throughout this account isn't confined to remote, uninhabited mountains, far from anyone's daily life. A meaningful share of it sits directly beneath the state's largest city. The same locked subducting boundary that produces those earthquakes is also, separately, the reason southern Alaska is lined with volcanoes, and the mechanism connecting the two is worth spelling out, because it shows the seismic and volcanic sides of this system aren't two coincidental hazards sharing a coastline. They're two different surface signatures of one buried sliding plate. As the Pacific Plate slides down into the mantle, it carries water locked inside its minerals and its sediments. Deep enough underground, heat and pressure force that water out, and it rises into the wedge of mantle rock sitting above the sinking plate. Water lowers the melting point of rock the same way salt lowers the freezing point of ice on a winter road, so mantle material that would otherwise stay solid partially melts. And that magma, being less dense than the rock around it, rises toward the surface through whatever cracks and weaknesses it can find. Draw a line above the point where the subducting plate reaches roughly 60 to 70 miles of depth, and that line traces almost exactly where a chain of volcanoes forms on the surface above it. Alaska's volcanic arc is the tectonics already described, made visible above ground. Rising through the crust, the same collision has already spent millions of years thickening and folding. The Aleutian Islands carry the clearest evidence of that arc, a chain of more than 40 active volcanoes strung along the curve of the subduction boundary, part of the broader ring of volcanic and seismic activity that circles the Pacific Ocean, known as the Ring of Fire. The islands carrying that arc are the geography made walkable, a chain of more than 100 separate islands curving nearly 1,500 miles out into the North Pacific, most of them treeless because of relentless wind and a raw maritime climate, rather than because the growing season is actually all that short. Shishaldin Volcano, on Unimak Island near the start of the chain, is one of the most symmetrical volcanic cones anywhere on the planet. A near-perfect cone, rising more than 9,000 feet directly out of the sea, and one of the arc's most consistently active vents, sending a thin plume of steam off its summit on most clear days whether or not it happens to be mid-eruption. Wind here can be its own hazard entirely separate from anything volcanic or seismic. Sudden, violent gusts called williwaws, driven by cold air pouring down off steep terrain, can appear across the Aleutians and the fjorded coast with almost no warning, strong enough to have capsized small vessels caught unprepared. A hazard local mariners have learned to respect as much as any wave or tide already described. Some of the Ark's volcanoes barely go quiet at all. Pavlov Volcano on the Alaska Peninsula is among the most consistently active in the entire chain, producing minor eruptions every few years without ever building toward anything close to Novarupta's scale, more a steady release valve than a single catastrophic event. Farther out in the Aleutians, Great Sitkin has spent recent years in a slow, ongoing eruption of its own, a lava dome quietly growing inside its summit crater rather than exploding outward all at once. A reminder that this arc doesn't just produce occasional headline disasters. It's doing something. Somewhere along its length, almost continuously. Even a volcano long, assumed to be finished, can show signs of quietly waking back up. Seismic instruments near Mount Edgecumbe, close to Sitka, detected a swarm of small earthquakes consistent with magma shifting beneath the volcano after centuries, without any recorded activity, even though nothing since has suggested an eruption is actually close. It's a small, recent example of how continuously this whole arc gets watched, and how little confidence anyone allows themselves that a volcano's long history of quiet guarantees anything about what it does next. Across the whole state, Alaska is home to more than 130 volcanoes and volcanic fields, and more than 50 of them have erupted within recorded history. The largest volcanic eruption anywhere on the planet during the entire 20th century happened here, when Novarupta erupted in 1912 near Katmai, ejecting roughly 3 cubic miles of volcanic material, more than 30 times the volume Mount St. Helens released in 1980. Ash from Novarupta buried a nearby valley beneath hundreds of feet of hot volcanic deposits so thick that steam still vented from the ground for years afterward, in a landscape later named the Valley of 10,000 Smokes, for exactly that reason. Novarupta's eruption didn't just bury a valley in Alaska either. The sulfate aerosols it threw into the stratosphere spread around the globe and measurably dimmed sunlight for months afterward, contributing to a cooler than average year across parts of the Northern Hemisphere. Logged in newspaper weather reports as far away as Europe at the time, even though almost nobody there knew where the eruption that caused it had actually happened. Nobody scientific witnessed the eruption directly, since the area was uninhabited at the time. But a National Geographic Society expedition led by botanist Robert Griggs reached the site a few years later and found a valley still venting steam from thousands of fumaroles across the buried landscape, a sight striking enough that Griggs's photographs and reports helped convince the federal government to protect the area, leading to the creation of Katmai National Monument in 1918, later expanded into the national park that exists today. The aviation risk that volcanic ash poses here isn't theoretical either, and one incident made that point about as clearly as it could be made. In December of 1989, Mount Redoubt, roughly 100 miles southwest of Anchorage, erupted and sent an ash cloud directly into the path of a passenger jet, a Boeing 747 flying at cruising altitude near Talkeetna. The ash choked all 4 engines simultaneously, and the aircraft dropped more than 2 miles in altitude before the crew managed to restart the engines and land safely in Anchorage, badly damaged, but with everyone on board alive. That single close call reshaped how airlines and air traffic controllers treat volcanic ash worldwide, and it's a large part of why the Alaska Volcano Observatory, a joint operation between the United States Geological Survey and state and university partners, keeps continuous watch on every historically active volcano along this coast, issuing aviation alerts the moment unrest shows up on a seismometer or a satellite image. Not every one of the state's historically active volcanoes carries real-time ground instrumentation either. The observatory prioritizes seismic monitoring toward volcanoes sitting closest to air routes and population centers, which means a meaningful share of Alaska's volcanic arc is watched mainly from orbit through satellite thermal imagery rather than through instruments planted directly on the mountain itself. Because a huge share of flights between North America and Asia cross directly over this volcanic arc, on the shortest available route, that monitoring isn't a niche academic concern. It sits directly underneath one of the busiest stretches of international air travel on the planet, watched around the clock by people whose entire job is noticing when this system starts to move. Volcanoes here can generate hazards that have nothing to do with lava or ash directly too. Augustine Volcano, an island volcano sitting in Cook Inlet, has a documented history of flank collapses, moments when a portion of the volcano's own unstable slope gives way and slides into the water all at once. And geologic evidence preserved in coastal deposits around the inlet shows that at least one of those past collapses generated a local tsunami capable of reaching nearby shorelines within minutes, far too quickly for any conventional warning system to help anyone standing on the beach. It's a second, quieter way this system converts one localized, sudden event into a wave, alongside the earthquake-triggered landslide that produced the giant wave at Lituya Bay described earlier, and a reminder that the ocean here rarely needs an earthquake specifically to turn violent without warning. Step away from the coast and the mountains, and the same climate contrast that split Cordova's rainforest from Fairbanks's near desert reappears in a different form underground, in the shape of permafrost. Ground that stays below freezing for at least 2 consecutive years qualifies as permafrost, and it underlies something on the order of 80% of the state, though not evenly. Along the north slope in the far north, permafrost is continuous, an unbroken layer running hundreds of feet deep in places. Through the interior, it turns discontinuous, patchy pockets of frozen ground interrupting warmer soil depending on slope, drainage, and how much insulating snow cover a given spot happens to collect. Along the storm-battered, relatively mild southern coast, it mostly disappears altogether. That distribution isn't random. It follows directly from the same moisture and mountain barrier system already at work, because the Alaska Range and the ranges further south intercept the warm, wet Pacific air before it can reach the interior and the north, leaving those regions cold and dry enough for the ground itself to freeze solid and largely stay that way for centuries at a stretch. Permafrost also builds its own distinctive landforms, visible from the air across huge stretches of the North Slope. Repeated seasonal cracking and refreezing of ground ice over centuries can build vertical ice wedges many feet across, and where those wedges intersect, the surface sinks into a honeycomb of polygon-shaped patterns, clearly visible from an airplane window. Elsewhere, pressurized groundwater pushing up beneath frozen ground can dome the surface into a pingo, a standalone hill sometimes rising well over 100 feet, built entirely from an ice core rather than rock, a landform that exists almost nowhere outside permafrost regions like this one. Permafrost holds more than frozen dirt. In many places, it carries a substantial share of ground ice, occasionally in wedges and layers thick enough to matter structurally. And when that ice thaws, the ground above it doesn't just get soft, it can lose volume outright and collapse, a process with the specific name thermokarst. Whole sections of forest can tilt and sink as the ice supporting their roots melts unevenly, producing what residents sometimes call a drunken forest. Trees leaning in every direction because the ground beneath them no longer holds a consistent shape from one trunk to the next. Black spruce, the tree most associated with this shallow, waterlogged permafrost country, has adapted to root sideways across the thin layer of soil that thaws each summer, rather than downward into ground that never fully softens, which is part of why a stand of black spruce leans and topples so readily once the ice beneath it starts to shift unevenly. The same wide temperature swings covered earlier compound the problem in a more mundane way, too, driving repeated freeze-thaw cycling near the surface that heaves pavement and foundations year after year, even where deeper permafrost stays intact. A slower, grinding structural cost that shows up on roads and building slabs across the interior almost every spring, cracked and patched and cracked again. Permafrost also functions as one of the planet's largest cold storage units for ancient carbon, holding the partially decomposed remains of plants and animals that have sat locked in frozen ground for thousands of years without fully breaking down. Estimates suggest Alaska's permafrost, alongside the rest of the Arctic's frozen ground, holds roughly twice as much carbon as currently sits in the entire atmosphere. As that ground thaws, the same microbial decomposition that stalled out in the cold resumes, releasing some of that stored carbon back into the air, which means the exact same permafrost machine responsible for the drunken forests and the eroding villages already described is also quietly wired into a far larger, planet-scale carbon cycle that most people never think to trace back to one specific stretch of frozen Alaskan ground. Permafrost and wildfire feed each other in the state's interior in a way that surprises people who assume fire and frozen ground have nothing to do with one another. The insulating layer of moss and organic soil sitting above permafrost normally protects the frozen ground underneath it from summer heat. But when wildfire burns that insulating layer away, the permafrost below is suddenly exposed to direct sun and warmer air, and it can thaw far faster than it would have otherwise. Alaska's interior regularly experiences some of the largest wildfire seasons anywhere in the country by total acreage burned, with some recent seasons scorching more than 5 million acres, and each one leaves behind ground more vulnerable to exactly the kind of thermokarst collapse just described. A second, less obvious way this state's fire and its frozen ground stay wired into the same feedback loop as everything else in this account. The same continental climate extremes play out every spring along the Yukon River, one of the longest rivers in North America at nearly 2,000 miles, draining a watershed that stretches across a huge share of the terrain collage already covered. Each winter, the river freezes solid enough to drive trucks across it, and each spring it breaks apart in a violent, compressed event rather than a gradual thaw. Ice slabs the size of small buildings grinding against each other and piling up until the whole river lets go at once, sometimes damming its own flow long enough to flood the town sitting above the jam. The town of Nenana turned the exact timing of that breakup into a tradition dating back to 1917. With residents betting on the precise minute a tripod set out on the ice will finally fall through, and the resulting century-plus of records has become one of the longest continuous data sets tracking how the timing of that spring breakup has drifted earlier over the decades. An accidental science project built entirely out of a betting pool nobody set up with research in mind. Engineers building the Trans-Alaska Pipeline in the 1970s had to design around the thermal side of that problem directly, threading much of its 800-mile route above ground on vertical supports fitted with heat-dissipating fins, specifically to keep the pipeline's own warmth from thawing the permafrost underneath it and letting the whole structure sink or buckle over time. That same engineering also had to account for the fact that the pipeline's route crosses the Denali Fault directly, and that decision was tested far sooner than anyone building it could have expected. When the fault ruptured in 2002, the ground on either side of the pipeline shifted sideways by more than 14 feet in a matter of seconds. At that exact crossing, the pipeline had been built on a system of sliding supports specifically engineered to let the pipe move with the ground rather than snap, and it worked. Oil kept flowing within days because the design had planned, years in advance, for the exact ground movement that ended up happening. That same earthquake didn't just move the ground either. It shook loose enormous avalanches and rockfalls across the range above the fault, some landing directly onto glacier surfaces and visibly altering how those glaciers flowed in the years that followed. A rare, directly documented case of a single earthquake reaching into the ice machine and changing its behavior in one specific mapped place. Ordinary buildings across permafrost country have needed their own quieter version of that same foresight for generations. Structures are commonly raised on driven piles or set on adjustable gravel pads, specifically so a gap of open air separates a heated building from the frozen ground underneath it. And where that gap gets skipped, whether through age, cost-cutting, or simple bad luck, the building's own warmth slowly thaws the permafrost below, and the foundation follows the ground down, unevenly, room by room. For some communities, this same set of forces has become a genuine, present-tense emergency, rather than a subject for study. Villages including Newtok and Shishmaref, both built on permafrost bluffs along Alaska's western coast, have watched the ground beneath them erode by tens of feet in a single storm season. As thawing permafrost weakens the coastal soil at the same time that a shorter sea ice season leaves the shoreline exposed to open water waves for more months of the year than it used to be, residents of both communities, most of them Yupik or Inupiat, voted to relocate their entire villages to more stable ground rather than wait for the alternative, a decision built on generations of direct knowledge about how this coastline actually behaves, not one forced on them by outsiders unfamiliar with the place. Long before any of the instruments or research projects described throughout this account existed, the region's Alaska Native peoples, including Unangax communities along the Aleutians, Sugpiaq communities around Prince William Sound and Kodiak, and Tlingit communities along the Panhandle, held their own detailed, generations-deep knowledge of how this coastline moves, floods, freezes, and shakes, built through lived experience rather than seismometers or ice cores. Modern instruments have added precision and a written record. They didn't discover that this land behaves this way. People living on it had already known for a very long time. It's one of the clearest human-scale consequences anywhere in this whole system, and it comes from the same permafrost mechanism already covered, colliding directly with a coastline that the region's own glacial and tectonic history built in the first place, long before anyone lived along it. Along Alaska's Arctic edge, on the Beaufort Sea, that same erosion has been measured directly, and some stretches of that permafrost coastline retreat by more than 30 feet in a single year, among the fastest rates of coastal land loss recorded anywhere on the planet. The mechanism runs in a fairly straightforward chain. Permafrost bluffs that once stayed frozen and solid through most of the year now thaw for longer stretches. Sea ice that used to buffer the shore from wave action now forms later and breaks up earlier, and open water gets more time each year to work directly on ground that's lost the structural strength the ice inside it used to provide. It's the same permafrost machine described a few movements ago, just running its most visible, fastest consequence directly into the ocean instead of underneath a highway or a pipeline. Return to the coastline itself, because the fjords carved by all that glacial erosion didn't just reshape individual bays, they multiplied the length of the coastline as a whole. Measuring a coastline is a strange exercise mathematically, since the answer depends heavily on how finely you trace every inlet and island. But by the standard federal accounting used by the National Oceanic and Atmospheric Administration, Alaska's tidal shoreline, counting every bay, fjord, and island edge, runs to somewhere close to 34,000 miles, comfortably longer than the combined coastline of every other state in the country put together. That number comes directly from the glacial carving already covered, not from Alaska's size alone. Fjords and inlets fold the coastline back on itself again and again, and an archipelago like the Alexander Archipelago in the southeast, itself largely shaped by past glaciation, multiplies the edge length further with every channel that separates one island from the next. That same fjorded, deeply indented coastline created a very different kind of consequence in 1989, when the oil tanker Exxon Valdez ran aground in Prince William Sound. The same glacially carved complexity that multiplies Alaska's coastline into the tens of thousands of miles also multiplied the difficulty of the cleanup that followed, since oil pushed by wind and current could work its way into hundreds of separate coves, channels, and gravel beaches that a straighter, simpler shoreline would never have offered it in the first place, turning a single spill into a problem spread across an enormous stretch of folded, complicated coast, rather than one contained stretch of open beach. Some of those glacially carved inlets do something else entirely. Once the tide starts moving through them, and it comes down to shape rather than location. A funnel-shaped inlet, wide at its mouth and narrowing steadily inland, can amplify an incoming tide the way squeezing a stream of water through a narrowing hose speeds it up. And if the natural rhythm of that funnel happens to roughly match the timing of the tide itself, the amplification compounds with every cycle, each incoming tide arriving a little stronger than a simple, unamplified tide would. Cook Inlet, and specifically its narrow arm called Turnagain Arm near Anchorage, is shaped almost perfectly for that resonance, and the tidal range there can reach close to 40 feet, the second highest tidal range recorded anywhere in North America, trailing only Canada's Bay of Fundy. The incoming tide arrives fast enough and concentrated enough that it forms a visible wall of water called a bore tide, sometimes several feet tall, that surfers and kayakers can actually ride up the inlet as it advances inland, chasing a wave that outruns most people on foot. The bore itself is a moving hydraulic jump, a sudden step change in water depth that holds its shape as it travels, the same basic phenomenon that shows up in miniature when water rushes across a flat kitchen sink, just scaled up to the size of an entire inlet by the volume of water Cook Inlet's geometry happens to funnel through it twice a day. The forearc basin that Cook Inlet occupies, the low, subsiding trough sitting directly above the subducting plate, is itself a product of the same tectonic system already described throughout this whole account, which means even the tides here trace back to the same underground engine as the mountains and the earthquakes, the same violent tidal mixing that produces the bore tide in Turnagain Arm, does something less dramatic but ecologically vital across Prince William Sound and the wider Gulf of Alaska coast, churning nutrient-rich deep water up toward the surface, where sunlight can reach it. That mixing helps sustain dense seasonal blooms of plankton, which in turn draw in herring, seabirds, and some of the largest concentrations of feeding humpback whales anywhere on the Alaska coast. One more food web resting on tidal mechanics, this account has already traced back to fjord geometry and forearc subsidence. Zoom out from any single mountain range or fault or inlet, and Alaska's geography stops looking like a state with unusually many mountain ranges crammed inside its borders and starts looking like exactly what it's, a collage. Alaska is built from more than 50 distinct terrains, chunks of crust with completely different origins and histories that arrived from elsewhere and got welded onto the edge of North America over roughly the last 160 million years. Wrangellia is the best studied of these arrivals. Rock samples pulled from across its range, from Vancouver Island up through southern Alaska, carry a matching volcanic signature and matching magnetic readings that place its original latitude close to the equator, meaning a single terrain, now split across a Canadian island and an Alaskan mountain range, spent part of its history thousands of miles south of where either piece sits today. The Alexander Terrane and the Peninsular Terrane, both also welded onto the growing edge of North America at different points, carry their own separate travel histories, distinct enough in their rock chemistry that geologists can still tell them apart from their neighbors even after tens of millions of years pressed together side by side. Not every terrain welded onto Alaska arrived as one coherent block, the way Wrangellia or the Yakutat terrain did either. The Chugach terrain, forming much of the mountain range that hugs the coast around Anchorage and Prince William Sound, built up instead as an accretionary wedge. Material scraped directly off the top of subducting oceanic plates over tens of millions of years and plastered onto the edge of the continent in overlapping slices, the same basic process still happening today at the Aleutian Trench. It's a genuinely different way of adding land to a continent than a single buoyant plateau jamming into the margin, closer to a bulldozer pushing up a pile of loose material in front of its blade, than to two solid objects colliding directly. And Alaska's coast happens to carry clear examples of both processes, sitting only a few hundred miles apart from each other. The same terrains that built Alaska's mountains also concentrated some of its most valuable mineral deposits, and the connection isn't incidental. Gold tends to collect in quartz veins formed where hot, mineral-rich fluids move through fractured rock during periods of tectonic stress, exactly the conditions produced when one terrain grinds against another or gets folded and faulted during accretion. The gold districts around Fairbanks and along the Juneau Gold Belt both sit inside terrains that were welded onto North America through this same collision process, and the deposits miners rushed to claim during the gold rushes of the 1890s and early 1900s trace their origin to the identical accretion history that built the mountain ranges sitting above them today. The terrain collage that makes Alaska's geography this complicated is the same terrain collage that made parts of it worth a fortune to prospectors who'd no idea what a subduction zone was and wouldn't have cared if they'd. Not every mountain range in Alaska belongs to the young, fast-moving system built by the Yakutat collision, and the Brooks Range in the far north is the clearest exception, worth returning to now that the terrain picture is fully in view. It formed from a much older collision, one that happened over roughly 100 million years ago, as a separate piece of crust jammed against North America's northern margin, long before the Yakutat terrain ever arrived farther south. The Brooks Range today sits quiet by comparison, its peaks worn down by hundreds of millions of years of ordinary weathering, rather than actively rising the way the St. Elias Mountains still are. Alaska's mountains, in other words, aren't one machine running everywhere in the state at the same speed. They're several separate collisions from wildly every different points in the planet's history that happen to have ended up sitting side by side inside the same modern borders, which is its own kind of extremity, even before any single range gets measured on its own terms. North of the Brooks Range, that same ancient collision shaped the sedimentary basin sitting beneath the North Slope, where layers of organic rich rock accumulated over hundreds of millions of years and were eventually buried deep enough and heated gently enough to convert into oil rather than being cooked away entirely. Prudhoe Bay, discovered there in 1968, became the largest oil field ever found in North America, and the resulting flow of oil down the Trans-Alaska Pipeline, threading past the Denali Fault on those specially engineered sliding supports described earlier, has shaped the state's economy and its politics for half a century since. It's a case where an ancient, quiet mountain range that stopped actively building itself 100 million years ago is still, indirectly, responsible for one of the more consequential resources found anywhere in the country. One of those welded terrains produces a volcanic anomaly that doesn't fit the tidy subduction story covered earlier, and it's worth including precisely because it doesn't fit cleanly. The Wrangell Volcanic Field, sitting inland from the main Aleutian Arc, hosts some of the largest volcanoes by sheer volume anywhere in North America, including Mount Wrangell, still capable of venting steam from its summit crater today, rather than sitting directly above a clean, uniform slab the way the Aleutian volcanoes do. The Wrangell Field appears to sit near a torn edge or a gap in the subducting Pacific Plate, where mantle material can flow around or through the tear and melt in unusual quantities. It's a reminder that even a system this well mapped still leaves open, honestly unresolved questions about exactly what's happening in the details several dozen miles underground. And geologists studying the region are still refining that picture rather than treating it as settled. The same thick, buoyant Yakutat slab responsible for the unusually fast uplift in the St. Elias Mountains also does something to the volcanic arc passing nearby, and it's close to the opposite of what built the Wrangell Field. Where the Yakutat terrain subducts, it does so unusually flat and shallow compared with ordinary ocean floor, staying too cool and too close to the surface to release the water that triggers melting in the mantle above it. That flattened, sluggish subduction appears to shut volcanism off almost entirely along the stretch of coast directly above it, producing a genuine gap in an otherwise continuous volcanic arc. The identical slab that jams the collision and builds the mountains fastest is also a short distance away. The reason a section of coastline that geometry alone would predict should be lined with volcanoes has almost none at all. None of the measurements running through this account arrived easily, either. Reaching most of the sites already described, the St. Elias interior, the Bagley Icefield, the upper reaches of the Denali Fault, means flying in on small aircraft equipped with skis or floats, camping on ice or exposed rock for weeks at a stretch, and hauling drilling and survey equipment across terrain that offers no roads and often no reliable weather window at all. The clean numbers presented earlier, the inch of uplift, the sixth of an inch of erosion, the fraction of a millimeter GPS stations can resolve, all sit on top of that unglamorous, physically demanding fieldwork, repeated year after year, by researchers willing to keep going back. None of what has been described is ancient history dressed up as current events. Networks of GPS stations bolted permanently into Alaska's bedrock track the state's crust moving right now, at rates precise enough to detect motion of a fraction of an inch across a single year. And the numbers those stations return match the story at every point checked. The coast near Yakutat rising, the interior sliding along the Denali Fault, the ground around Glacier Bay springing upward as the ice above it keeps thinning. The instruments making these measurements possible are more sensitive than most people assume. A continuously operating GPS station bolted into bedrock doesn't just report a location the way a phone does. It tracks the exact phase of incoming satellite signals over months and years, filtering out atmospheric noise and orbital uncertainty until what's left is a position accurate to a few millimeters, repeated day after day, until a trend line finally emerges from what would otherwise look like meaningless scatter. Satellite radar interferometry, commonly called INSAR, fills in the gaps between individual GPS stations by comparing radar images of the ground taken from orbit weeks or months apart, revealing surface deformation, a volcano's flank slowly bulging before an eruption, ground subsiding after an earthquake, across an entire region at once rather than only at the handful of points where an instrument happens to be physically bolted down. That's the level of precision it takes to say with real confidence that one stretch of coastline is rising by an inch a year, while another, a few hundred miles away, is doing something else entirely. Satellite instruments now watch this whole system from orbit too, filling in the space between individual GPS stations and glacier stakes. Landsat imagery, collected continuously since the 1970s, lets researchers compare a glacier's exact outline year over year across the entire state at once, while more specialized laser altimetry missions measure surface elevation changes precise enough to calculate how much ice mass an ice field has gained or lost in a single season, without anyone needing to physically stand on the ice at all. A satellite mission called GRACE, flying in tandem pairs that measure tiny changes in the pull of gravity beneath them, has independently confirmed the scale of ice loss across Alaska's glaciers from orbit, detecting the spacecraft's own path nudged by however much mass, in the form of ice, happens to be sitting on the ground below at a given moment. It's one more example of how many independent instruments, GPS on the ground, cameras on satellites, gravity measured from orbit, all end up describing the same conclusion from completely different angles. Much of the detailed mapping of the Aleutian Trench and the offshore Yakutat structure, meanwhile, comes from research vessels like the Sikuliaq, operated by the University of Alaska, which tows sonar and seismic equipment along the seafloor to build the kind of high-resolution picture a satellite alone can't provide, translating an invisible, miles-deep trench into a chart geologists can actually study. Alaska is a landscape still under active construction, not a finished scene that happened to end up looking dramatic, with the same instruments that map the mountains today capable of quite literally watching them grow between one field season and the next. Pull one more thread outward before drawing all of this together, because the same Gulf of Alaska storm engine that feeds the state's glaciers and its rain-soaked coast doesn't stop mattering at Alaska's own borders. The Aleutian Low is one of the dominant, recurring pressure centers shaping weather across the entire North Pacific, and its strength and position in a given winter influence storm tracks and temperature patterns as far away as the continental United States. Meteorologists, watching how that low behaves in a given season, are, in a real sense, reading an early signal for weather patterns that'll eventually reach much farther south. The same machine that's busy building Alaska's mountains and feeding its glaciers is wired into a system that reaches well past the state's own coastline and into forecasts made thousands of miles away by people who may never think about Alaska at all while reading them. An unusually strong or displaced Aleutian Low in a given winter is one of the signals meteorologists watch closely when forecasting whether the Pacific Northwest and California are heading into a wetter or drier season than average, since the same pressure system steering Alaska's storms also helps steer the broader jet stream pattern that decides where those storms go next. The consequences of all this ripple outward into the parts of Alaska people actually depend on day to day, not just into abstract measurements read off an instrument. Rivers fed by glacial meltwater carry more than water alone. They carry the fine sediment that erosion grinds loose from the mountains too. And that sediment load shapes river channels, deltas, and near-shore ocean chemistry in ways that many of Alaska's salmon runs have adapted to over thousands of generations. The Copper River earns its name from deposits the Ahtna people mined and traded for copper long before European contact, or concentrated by the same volcanic and hydrothermal processes already described, building the state's gold districts elsewhere. The Kennecott mines further up that same river later became one of the richest copper operations in American history during the early 20th century, extracting ore rich enough that some of it reportedly needed no smelting at all before shipment. One more economic thread running back through the same terrain collisions that built the mountains standing over the mine today. That same river, fed directly by glaciers off the Chugach and Wrangell Mountains, also produces salmon runs prized specifically because of its glacial characteristics, and the fishery built around them opens every spring to real anticipation up and down the west coast, with prices at markets shifting the moment the first catch is confirmed. Bristol Bay, further west, hosts the largest sockeye salmon run on the planet, an industry valued at more than $2 billion in some recent seasons, once processing, shipping, and related jobs are counted, resting on a watershed shaped by the same glacial and tectonic history running through this entire account. Alaska's state constitution specifically requires fisheries like this one to be managed for sustained yield, a legal mandate written directly in response to watching other fisheries elsewhere collapse from overharvesting. One more way this state's relationship with its own geography has been written into policy rather than simply left to chance. None of that economic value exists independently of the mountains, the ice, or the erosion. It sits downstream of all three, literally as well as figuratively, carried to market on water that started as snow, on a mountain, most of the people eating that salmon will never see. Salmon is only part of a much larger picture. Alaska's commercial fishing industry as a whole, spanning salmon, pollock, crab, halibut, and cod, regularly ranks as one of the most valuable seafood economies of any state in the country, and nearly every part of it depends directly or indirectly on the same glacially fed rivers, tidal mixing, and productive continental shelf that the tectonics and the ice already covered spent this whole account explaining. The seismic side of the story left its own lasting mark well beyond 1964's immediate destruction, too. Building codes across seismically active regions of the United States were meaningfully reshaped by lessons drawn from how structures failed, and in some cases survived, that Good Friday engineers specifically point to Alaska's experience when discussing Seismic Zone 4, the strictest category in the codes, later adopted across much of the earthquake-prone western United States. A classification requiring structures to survive shaking intensities that 1964 proved were more than theoretical. They'd already happened, in this exact place within living memory. Those revised standards are a large part of why the 2018 Anchorage earthquake, 20 Icarus Skalmainik nearly as strong in local shaking as some historically deadly quakes elsewhere in the world, killed no one at all. A disaster confined to one corner of one state ended up changing how engineers designed buildings on the opposite side of the country, decades before most of those engineers had ever set foot in Alaska themselves, working from lessons pulled out of a place they'd likely never visited. One more force has started pressing on this entire system at once in recent decades, and it's worth naming plainly, rather than folding it quietly into everything already described. A warming climate doesn't touch just one part of this machine. It touches nearly all of them simultaneously, precisely because they're wired together in the first place. Warmer air melts glacier ice faster, which accelerates the isostatic rebound already measured near Glacier Bay, feeds more sediment and fresh water into the same rivers the salmon runs depend on, and shifts more of the region's precipitation toward rain instead of the snow that used to feed the ice in the first place. The same warming thaws permafrost faster, accelerating the coastal erosion measured along the Beaufort Sea and adding urgency to the kind of relocation decisions Newtok and Shishmaref already made. None of these responses are separate stories that happen to share a warming trend. They're the identical mechanisms already covered in this account, all being pushed by the same external nudge at the same time, which is itself some of the clearest evidence available that this really is one connected system, rather than a coincidence of separate records sitting near each other. Climate projections for the region generally point toward continued glacier thinning, further permafrost loss, and a wetter, stormier Gulf of Alaska overall in the coming decades, though researchers are careful to note that individual glaciers and individual storm seasons will keep varying considerably around that broader trend rather than moving in lockstep with it every single year. Other subduction zones prove the point by falling short of it in their own specific ways. Chile runs on a broadly similar system and produces earthquakes on the same scale, including the largest ever instrumentally recorded, but it doesn't carry anything like Alaska's ice, because the moisture and cold needed to build glaciers this size simply aren't stacked on top of the tectonics there the way they're here. Japan sits on its own dense earthquake and volcano subduction zone, but its mountains are older and gentler, without a young, buoyant terrain forcing uplift at anything close to Alaska's pace. Other places on Earth get one or two pieces of this machine running at a serious scale. Very few get all of them layered on top of each other inside the same few hundred miles of coastline, running off the same buried plate at the same time. Add it up, and none of the individual superlatives scattered through this account were ever really separate facts competing for attention on a list. The uplift and the ice are opposite ends of one feedback loop, weighing each other in something close to real time. The storms and the mountains are cause and direct effect. The earthquakes and the volcanoes are two different surface signatures of one buried sliding plate. The permafrost and the rainforest are two outcomes of the same moisture being unevenly rationed by the same mountain wall. The fjords and the record tides share a single origin in glacial carving and tectonic subsidence. Pull on any one thread in this account, and nearly every other thread in it moves with it. That interconnection, more than any single number along the way, is the actual mechanism behind a title like this one. One relatively compact tectonic setting, a buoyant terrain jammed against a continent, sitting directly beneath one of the wettest storm tracks on the planet, is generating all of them from the same source at once, faster than almost anywhere else geologists have found to measure it. Rather than Alaska simply happening to hold several separate world-class extremes that landed near each other by chance. That's also, honestly, the more interesting version of the claim than the one the title seems to promise on its own. A state that simply held the tallest mountain, or the biggest glacier, or the strongest earthquake, would just be a list of records. Interesting the way a trivia card is interesting, good for a single fact and nothing to connect it to. A place where the mountain, the glacier, and the earthquake all trace back to the identical few miles of buried moving rock is closer to watching a single, unusually fast, unusually visible piece of how this planet actually operates, running out in the open rather than hidden under an ocean or stretched out over geological time so slow no instrument could ever catch it moving in a human lifetime. Most of the planet keeps this machinery decently hidden, tucked under oceans, spread across whole continents, or slowed down to a pace no field season could ever register. Alaska just happens to be the one place running it fast enough and close enough to the surface for anyone paying attention to actually watch it happen. So if there's one honest way to leave this, it's with the shape sitting underneath every number that appeared along the way, not with a bigger figure or a stranger fact than the one that opened it. Somewhere near the coast tonight, rock is being pushed upward by a collision that never lets up. And ice sitting directly on top of that same rock is cutting it back down at very nearly the same rate, and neither side of that exchange is going to finish anytime soon. Everything else covered here, the volcanoes, the earthquakes, the frozen ground, the impossible tides, is what it looks like when that one underground argument between uplift and erosion spills out across an entire state's surface. Nothing about that argument is finished, and it isn't waiting for anyone's permission before it continues tomorrow morning, the same way it's every morning before this one. If part of that surprised you, or if there's one piece of this machine you'd want a full episode built entirely around, the earthquake, the glaciers, the volcanoes, say so in the comments, because that's honestly what decides what gets measured next. Hit like if the uplift versus erosion tug of war actually changed how you picture this state, and subscribe if you want to keep watching ground that's still rebuilding itself in real time. There's another restless piece of coastline waiting for you next.